So there's something funny about presenting in this format because the topic of the talk is learning from mistakes, but it's this unidirectional talk. So I do want your comments and interruptions because that's the obvious nature of learning from mistakes. It involves multiple people. It's when we find our own mistake, um, no one even knows there is a mistake unless we first publish something wrong first. And then once we've published it, then people notice it and so forth. So it's an active process. I also want to thank the organizers because it's a privilege to be able to reach a wide range of people who I wouldn't necessarily see showing up to my classes at the university. I will tell you some stories about mistakes I've made, some stories about mistakes other people have made. From that, we'll try to derive some general principles and then think about how we can change our workflow. Now, I think at this point you think I'm going to say change our workflow so we won't make so many mistakes, but actually I want to change our workflow so we can learn from our mistakes. Mistakes are not something to be avoided. The only way to not make mistakes is to not do anything. So mistakes are an opportunity. They're a good thing, not a bad thing. So first, I'll tell you about the worst mistake I ever made, I think, and wasn't a mistake maybe at the time, but in retrospect it was. In 1994, a colleague and I published an article in the American Political Science Review called Enhancing Democracy Through Legislative Redistricting. And this was a paper, well, it was very successful. It won an award in political science. I was invited to speak in England about it. We were mocked in the House of Commons about this paper. Like one of my biggest heights of fame right there. Had a lot of influence in political science. I'll tell you briefly about it. We're trying to resolve some paradoxes of understanding redistricting. So people talk about redistricting, politicians redrawing the district lines. It's called gerrymandering. And it was believed that there were two things that politicians would do. One is that they would draw the district lines to help their own party and hurt the other party. The second is that they would draw district lines to preserve incumbents, to keep themselves in power. Well, there's in some sense no paradox yet. Well, one paradox is that when my colleague talked to actual state legislators, they hated the redistricting process. They didn't like it. They would regularly propose solutions that didn't involve any redistricting at all. They couldn't stand it, which is kind of funny if you think of it as this opportunity for them to manipulate the system. So we looked at empirical data we looked at all the state legislatures that had single member districts in the 1970s and 1980s. And in each of these legislatures, we had measures of partisan bias and electoral responsiveness. So partisan bias would be a positive number if it favors one party or negative if it favors the other. Electoral responsiveness is how responsive the election outcome is to your vote. What we found was that that redistricting had very small effect on partisan bias. It had some effect, but only 1 percentage point. So controlling the districting was only worth about 1% of the seats in the legislature for the party. Not a huge amount. With responsiveness, we found that compared to elections with no redistricting decreased responsiveness. It was increased responsiveness. That is, after redistricting, the election was more responsive than before, which is not what people were expecting to see. Well, we resolved this paradox by recognizing that redistrictors act under a large number of constraints. They have to have population be equal in each district. That's one reason they hate districting, is because they'll lose people or gain people from other districts and have to keep campaigning again, which they don't really like to do. Also, there were judicial constraints, because when a redistricting plan was too extreme, it would be thrown out by state courts, and then it would have to be redrawn. So we wrote this paper, Enhancing Democracy Through Legislative Redistricting, a big paradox. Gerrymandering is not so bad. We got a lot of attention, a great success. That was my biggest mistake. And the biggest mistake is if you follow American politics now, you know that extreme partisan redistricting, gerrymandering, has got much worse. There are states, famously North Carolina and Wisconsin, which have been gerrymandered almost out of recognition. Other states with very extreme gerrymanders, real actual decrease in democratic responsiveness. This is a real problem. Redistricting really is now used to lock in a system. It's used to lock in a party. So we were wrong. Well, how are things changed? There's reasons why we're wrong. How have things changed? Well, for one thing, they're better data, better computers. It's actually possible for like people with technical skills like me, but they're like bad guys who work with the data and try to make gerrymanders and do unfair redistricting. It's just a lot easier to manipulate than it used to be. The second thing is there's more partisan polarization. So in the past, one risk of gerrymandering, one way to gerrymander is you give your party a bunch of close districts. So you win a bunch of elections like 60-40, 55-45, and then you take all the votes for the other party and you put them in districts where they're winning with 90 or 100% of the votes. They're wasting their votes and you're winning efficiently. That's how you gerrymander. But in the past, if you give yourself a bunch of 60-40 districts, there is a risk that the next election there could be a swing and you could lose them all. Congress members, legislators didn't want to be in such close districts. Now with polarization, each election is very similar to the last. And so you can actually give yourself a close district and know that you can have a high confidence that you'll keep winning. So it makes it easier to gerrymander. The next thing is increasing partisan polarization more generally. So there's more of an anything goes attitude. In the past, a lot of actual politicians did not want to manipulate the system because they felt it was cheating. And there was kind of gentlemen's agreements sometimes to try to be fair to the other party. While with partisan polarization, as you see in the headlines, there's a lot less of that. The next thing is there is a decline in incumbency advantage. So back in the 70s and 80s, people who were already in office would tend to stay in office. In more recently, incumbency advantage is lower. And what that means is one of the main effects of redistricting was basically motivating incumbents to retire. So in the past, you'd redistrict, some people would lose their districts, a bunch of people would retire, it would shake up the system. One reason why redistricting made the system more fair and more responsive was because it got rid of a bunch of incumbents. Nowadays, incumbency advantage is not such a big deal, so getting rid of incumbents doesn't have this effect that it used to have. So one of the beneficial effects of redistricting is no longer there. Finally, there's reduced judicial scrutiny. So I think you've been hearing about the Supreme Court every now and then in the news, and you know the Supreme Court is much more partisan than it used to be. And in particular, courts at all levels are less likely to throw out districtings because of gerrymanders. And so that's one less constraint on the system. Okay, so that's all changed. We published an article in 1994, and things changed after 1994. So what did we do wrong, right? We talked about the past. Well, for one thing, we wrote our abstract in the present tense. So we wrote, gerrymandering biases electoral system in favor of the party that controls the redistricting as compared to what would have happened, but any type of redistricting reduces partisan bias as compared to an electoral system without redistricting. So what we said is redistricting reduces partisan bias. That's a false statement. What we should have said was redistricting reduced partisan bias. Was a statement about the past. Now that just sounds silly, right? Like people write in the present tense when they write research articles. We found that when you add more sugar to the mixture, it changes its viscosity, whatever people say but that's because the idea is that the laws of chemistry are not changing from one day to the next. Political science, things change. In economics, things change. When we're writing about the past, we should say we write about the past. Now, why would that make a difference? Who would have noticed that? Because had we written that in the past, then we would have thought, well, what about the future? And then we could have thought, now we might have just said, we expect these patterns to continue for the future. But maybe just thinking about the question of what will happen next, maybe we would have thought, well, assuming incumbency advantage stays large, assuming that judicial scrutiny remains, then we predict blah, blah, blah. So research papers, especially in the social sciences, are predictive. They have to be, almost always we care about the future. The data are always about the past. So there is this thing, and we got it wrong. And I did not think about this until I was reading the newspaper one day about the redistricting, the gerrymandering in, I think, North Carolina. And then I felt really bad that I wrote this paper and we went around the country telling people, ha, 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 redistricting isn't so bad. And we were wrong. Okay, so that's mistake number one. For mistake number two, I'll share a slide. Okay.
Andrew, there is a question from the audience.
Okay.
Margaret, she asked, like, define responsive.
Responsiveness is defined, it's basically, it's the expected value. Well, it's the derivative of the expected number of seats your party wins in the legislature with respect to the number of votes that your party gets. So higher responsiveness means the same swing in the vote will create a larger swing in seats. So like if redistricting increases responsiveness, then that sort of contradicts the theory that redistrictors are there to save their own seats because look, they're creating, but again, that was in the past. So in the past, redistricting increased responsiveness largely because a lot of incumbents would retire and their seats would become more competitive. Okay, I will share slides just briefly. Most of the talk is not slides, but I have a couple for you. Okay. I was contacted I'm just trying to make this like look good for you here. I was contacted a few years ago from some people from the Wikimedia Foundation, and I think they actually are volunteers. They're just trying to help Wikipedia stay afloat. So as you perhaps know, if you've ever used Wikipedia, every once in a while they have a nag screen saying that if only a few percentage of people would contribute $3, then Wikipedia will stay afloat. They do that. They A/B test the hell out of this. Now, why? Because it's free. So once you're doing an online experiment where you're randomly giving people a nag screen. So of course you can randomly give some people nag screen A and some people nag screen B and see which one does better. So you can just test anything. It's free. This is not like a medical experiment where you need consent from people and where there aren't that many patients around. You're doing this on millions of people. So you might as well. They called me up, or I guess they sent me an email asking for my help because they said they're having a problem that they were running experiments and getting implausibly large estimates. And they knew that I had done research on how people get implausibly large estimates, which is indeed one of my research areas. And could I help? So of course I was happy to help for free. It's Wikipedia, right? Like they're the good guys. I want to help. Wikipedia is still the good guys at the end of the story, just to let you know. That's the twist, is not that like, you know, that they ate my cat or anything like that. They're great, okay? So here's an example. There were two nag screens. One had round corners, which was the default. The other had square corners, which was the other option. About 1 million trials, or about 2 million trials were done. So it was done 2 million people. Half the people got the ordinary, half got the square corners. Then the estimated result was here. The success rate, this is I think that actually literally the percent of people who clicked through and gave money was 0.51%, 0.5% in the control group and 0.43% in the treatment group. Well, that's a lot lower. It's actually 15% lower. 0.43% is 15% lower than 0.51%. And look at their 95, well, their p-value has a lot of zeros. Their 95% interval goes from -19% to -11%. Okay, so the first thing is, okay, this cannot be explained by selection bias, p-hacking, anything like that. They did an A/B test. you can keep your file drawer open between now and the end of time, and you're not going to get something that's whatever this is, 7 standard errors away from 0. Like this is something real. Well, it doesn't necessarily mean the nag screen made a bigger difference, but something, the null hypothesis is way off. Okay, there really does seem to be a big effect. First thing I did was check the algebra. I computed the square root of p times 1 minus p over n on my own computer and checked, and indeed this looked right. Multiple testing correction has nothing to do with anything, because no multiple testing correction is going to get you from 8 standard errors away from 0. Like that's a huge thing. Big effect. So I said, well, I don't know. I said, I find it implausible that this small intervention would have a 15% effect, but I could be that the effect varies. It could be really high one day, really low the next day. Maybe it's high during the day, low during the night. And so I would say, like, you might want to like repeat this on different conditions and see. And my guess is if it's 15%, it could be minus 10% another time. It could fluctuate a lot. I don't think you might not want to take this too seriously. And they said, well, they weren't sure about my potential answer, because they said there is evidence like giving is correlated with time of day. So people at night give less than people during the day, but they haven't found big differences like of treatment effects when the treatment's done at different times. So we had to think further. So I want it here. First, I'm going to show you, these are the 2 treatments, just so you'll see. You don't have to stare at them. It's really just round corners or square corners on the nag screen. Like this is, the treatment effect should probably be 0, but you don't know it would be 0, right? You could come up with a theory for why the round corner, like the square corner, seems more serious, and that could make a difference. It's, again, A/B testing is free, so why not do it? Okay, so back to their data. I want you all to spend 30 seconds looking at this and see if you see what's wrong, what seems to have gone wrong here. I'll give you a minute. Approximately a minute. I don't have a timer here. Come on, keep looking. Keep looking, you can find it. Okay, with hundreds of people, okay, probably some people have noticed. We don't have the live participation part, or I have you do it in pairs. The thing that was suspicious to me is the number of trials. So randomized experiment, you'd expect to have equal number of trials in the 2 groups. Not literally equal, but you'd expect the difference between the 2 groups to be within the binomial distribution. But it's 1.08 million in one group, or was it? It's hard to even read. Yeah, it's 1.08 million in one group and 0.95 million in the other. That's much more variability than you'd expect by flipping coins. Now, if the ratio were 2 to 1 or 3 to 1 or 10 to 1, I would say, oh, that was just the design of the experiment, right? That could be. But who would design an experiment to do to have that thing? So I asked them if they had data on the time of when the study was done. Okay. So here it is. I redrew the graph to make it pretty, but they sent me this was the number of participants in the experiment every minute of the experiment from 4 p.m. to 4 a.m., which is how long they ran it. So you see at the beginning, the blue is a control condition and the red is the treatment condition. So at first the experiment goes online, and then it's really literally 1 dot per minute here. There's about almost 4,000 people per minute hitting the nag screen. I don't know, it's going up and down, something's happening, like who knows what. But then around 7:30, all of a sudden, a lot more are getting the treated one, and then something happens like at 7:45, and then something happens at 9, and then it's not balanced, right? Okay. Do you remember I told you people gave less at night than in the day? So the treatment is happening more at night, and so it's lower. So, okay, that's what happened. So the they made a mistake, right? I mean, this is a mistake that was made, and the mistake, and I don't know what it was. I don't think they ever tracked it down because you could just do another experiment, but you could say like, what are the mistakes being made here? Um, so yeah, somehow I don't know whether the randomization got messed up or whether maybe it was like people, equal numbers of people received it, but then the messages back got trapped. And obviously something wrong in the engineering. But it's an interesting example because it gives me some statistical insight. This is the number of requests. This is not the data of whether people contributed. Um, if you had those data, which they didn't seem to have anymore, then you could actually estimate the effect of the treatment by adjusting for time. So you could just do an analysis adjusting for time. Like you might, in this case, you have no data here. So you'd probably do is some sort of matching, right? You just match everything and you'd throw out, so you'd throw out some of the extra, or I don't know, you just match them by time, basically. It would be very easy to do because you have so much data, and then you'd estimate that. Well, I probably wouldn't recommend that either, because if there's imbalance over time, there could be imbalance over other factors too, right? Who knows what's going on. But it kind of gets you thinking about stuff. It definitely helped me as a statistician, because after doing this, now whenever I have data, I always say plot the data over time. And actually, that's one of my big research areas now, is integrating time into everything I do. And I'm more and more, I have another talk about that called It's About Time, which I won't give you here, but it's all about how many paradoxes of statistics can be resolved by including time in the model. So yeah, a story of a mistake.
Dr.
Yeah,
Gelman, if I may interrupt, there is a question
yeah, please.
from the audience. So it says, what made you first think, let's look at the response rate over time, the imbalance of the number of trials, or something else?
Oh, well, I looked at this is all I had. So my first thought was, I don't like p-values. I want the estimate, the standard error. My second thought was maybe the standard error is wrong. My third thought was so those I could check myself. The third thought was this hypothesis that the treatment effect just varied a lot, but they said they didn't believe that. And so then what else is there? So I just started staring at this, and I noticed these two numbers, and they weren't balanced. So yeah, you could say there's other lessons here. I mean, there's a lesson that it's good to have these intermediate things. Like I hate tables. I like graphs and not tables, but looking at numbers can help. Sometimes you see weird things in the raw numbers. And so looking at more is good. How did I think of doing time? I just like, I don't know what made me think of that. Or maybe it was their idea. I'm not sure, but it's like you should always look at time. Data come in time. So like almost that's one variable that exists in almost every problem. Mm. Okay.
There's another question that was, I think, corresponds to your previous story, and then it says like sorry, my by redistricting, do
Yeah.
you mean redemarcating the districts?
Yeah, redistricting means, sorry, I should have defined it. This is where in a live talk, I'd see people with a puzzled expression on their face. Redistricting, yeah, it's redrawing the district lines. So you'll have a state, and the state is divided up into districts, and each district will send one representative to the state legislature. Every 10 years, they have to redraw the district lines because populations change and districts have to have equal population. There was a Supreme Court case in the early 1960s saying that districts had to be equal population. Before that, they didn't. But they redistrict every 10 years based on the census, which happens every 10 years.
Thank you.
Okay, now I have another story. Another mistake. This is a mistake that I made. It makes me look kind of stupid or silly or something. Okay, it's hard to read. It's hard to read these words probably. And so I'm not going to ask you to try to read the words. I made this. I'll tell you what these maps are. They're from the 2000. They're from election polls from 2008. And I will just say that I think I'm more aware of that people view things horizontally. So I like make my displays differently than I did back then. Um, these are maps of the 2008 presidential election, which was Barack Obama, the Democrat, who's represented by blue, and John McCain, the Republican, who's represented by red. Now, I want you just to look at the left column first. The left column is our estimates based on polling data of who would have won each state if you'd only counted people in the highest range of income, upper middle, lower middle, and lower income. So according to the maps on the left, if the election of 2008 had been just people in the rich people, or the top 5% of income, according to polls, John McCain would have won almost every state. He would have lost New York and California and Illinois and a few others, but he would have won most of the states. Now, as you go down lower and lower income, Barack Obama would have done better and better. And if the election had been held only among poor people, it says Obama would have won 46 states. Now, we don't know, because we don't know from the election of we don't know how rich and poor people are who vote. So this is based on polling data. So we fit a statistical model to polling data using multi-level regression and post-stratification. And you find it's kind of interesting, because you find that richer people are more likely to vote for the Republican, but it varies by state. In some states, there's big differences between how rich and poor people vote, and some there aren't. And I wrote a book about that. Well, I made those graphs on the left, and then people kept saying, well, okay, that we want to know about white people. So most voters in the United States are white. White is slang for European American or something like that. Like, we're not really white, I guess, but that's the term that gets used for my ethnic group, white people. People want to know, because lower income, yes, Barack Obama would have crushed among poor people, while a lot of poor people are ethnic minorities and more likely to vote for the Democrats. So people are interested in whites. So the second column of maps is what would happen among white people. And there you still see the pattern. Among white people, among rich white people, John McCain really would have crushed. He even would have won California, according to this. Now, if you go down among poor white people, well, Obama still, I think, would have won a majority of the electoral votes based on that map, but it's kind of close. So it was kind of closer to 50-50. Maybe Obama had the slight edge among poor white people. So there is a difference, income gradient in voting among whites, but it's a little bit different. It's a little lower than among everybody. So I was very proud of these maps, and I posted them online. I posted them on the 538 website, in fact. And it got some attention. People said cool maps, which is what I liked. But then some people said stupid maps. Like, hey, stupid maps, man, those are really stupid. These are terrible. And they were kind of rude. Like, the commenters were like, oh, your maps are, you're an idiot. So why am I? So they had issues with particular states. So New Hampshire, for example, it's hard to see this. You can stare at this, but if you look carefully, it shows that John McCain is doing better it shows that Barack Obama is doing better among rich voters than among poor voters in New Hampshire. Well, it could have been, but if you look at polling data, the polling data don't show this. According to the polling data, Barack Obama there's exit polls in New Hampshire. According to the polling data, Barack Obama did better among poor whites than among rich whites. Well, in New Hampshire, most people are white. So it's contradicting the polling data, which is kind of weird, because these maps are based on polling data, right? So it's like, there was something, Michigan, from polling data found that among whites, Michigan was very closely divided. Well, Obama easily won Michigan in 2008 because he crushed among the minorities, but it was about 50-50 among whites. According to our map, Obama was winning Michigan among all white categories. And that just seems like kind of funny. If he's doing better among poor than rich, then how come? And then there are some issues with other states that were inconsistent with the polling data. So it turned out that I was wrong. that these critics were right. Well, these critics weren't right about everything, because I won't go into all the details. Some of the cases where they said I was contradicting the poll data, my analysis was doing better than the polling data because it was smoothing it in a reasonable way. The polling data are noisy and the polling data need to be adjusted. So it's not that not every criticism they made was correct. However, they were onto something. And I'll tell you why. There were a bunch of things going on, but there are really two fundamental problems with this analysis. The first is the display. It's red or it's blue. It's nothing in between. So you lose nuance, and it's hard, like, to say, like, Michigan always, well, were they close? Like, everything, this map, it's so much of the communication is based on whether it's 50.01 or 49.99. So I'm really communicating, like some things aren't. Like, okay, Montana, well, John McCain was going to win Montana. That's up there. That's clear. Okay. Barack Obama is going to win California. But the close states, the states that are kind of flipping, they're the ones you're interested in. So paradoxically, this map gives you very good signal on cases where you don't need it. Like, oh, California is going to go for the Democrats. Right? But for cases where you really care, because it might be close, like what's happening in Missouri, what's happening in some close states, map is magnifying noise. So that's problem number one. It's bad at communication, which is a problem because the whole goal of this map was to communicate. Otherwise, it could just give them a pile of numbers. Right? The other problem with the map is more subtle. And the question is, why did I show everybody in whites? Why didn't I show say everybody, why didn't I do whites, blacks, Hispanics, other? Why didn't I just do whites and non-whites, right? Why did I not do non-whites? Why aren't the non-whites here? Well, it's because what I did was I fit the analysis to everybody. Then I did my entire analysis to whites. That's easy to do because almost all the survey respondents, 80% of the survey respondents are white, so I could do the analysis. Non-whites are 20%. If I were to do my model on only 20% of the data, it would have big problems. So it would need to put in more information. It would do too much smoothing. There's issues. The map for non-whites would be terrible. So I didn't do it. Okay? But the trouble is I fit separate models to whites and to everybody and to whites. And when you fit one model to everybody and another model to whites, there's nothing making them consistent. And so it turned out that what I ended up doing was I was estimating, I think, that 108% of non-whites I think I was estimating that 108% of non-whites in New Hampshire were voting for Obama, something like that. Like implicitly. That is, I estimated New Hampshire, I estimated the whole country for everybody. Then I did for whites. But like there was no constraint that the total number of white votes for Obama has to be less than the total number of votes for Obama. Like it's just not there. It's not a constraint. And so because of that, because the model's doing all sorts of smoothing, it's kind of smoothing them to different places. And it would be like as if you're doing something like the consumer price index and you have you use different consumer price indexes for different states and then try to compare, right? It happens a lot in applied statistics. There's a numerator and a denominator and they're computed in two different ways and then they're incoherent. But this time I did both. Right? So I swallowed my pride and spent a few months working hard. And I made prettier graphs. And also I expanded my model to allow an interaction between income and ethnicity. But that took a lot of work. I mean, it was not like this map, I made the first map and people loved it so much that I pushed a button and made the second maps. But to do the new thing, I needed to actually do some research. I had to expand my model. I had to fit a model with an interaction. I ended up changing the model. Anyway, these are the results. I'm not going to go through them to say that you can see I now use the nuanced color scheme. You could look at Michigan and you'll see that Michigan it is actually kind of varying in its intensity for Obama. Michigan is very slightly red, and then down here, Michigan is slightly blue. If you stare at it, you can see these things. So I fixed the problems. So that was just great. Well, one message is I had to listen to the critics, even though they were rude to me, and they didn't even have a PhD. Like they didn't know anything. People without a PhD, just some bozos on the internet, some bloggers being mean to me. but yet I learned something because it was an opportunity. They were doing me a favor by just like if you're about to cross the street and a bus is about to run you over and someone says, "Hey, asshole, stop, there's a bus," and you don't get run over, you shouldn't be like, "Oh, you called me an asshole." Like, no, like you saved my life, right? Okay. If saying "hey, asshole" is the way to get my attention, go say it, call me an idiot. Don't be like so damn polite I don't notice that you think I made a mistake, right? Sure, you can say, "Excuse me, sir, I would like to warn you that if you keep stepping forward, you might get your ass run over," and not already be dead, right? So good for them. Thank you for them for doing that. Okay. Um,
Hi, Andrew.
yes.
There's a couple of questions if you don't mind.
Yeah.
So the first is pulling data before the election, presumably, versus what the other kind of data?
Oh, well, we can make these, we made the map, I believe we made these graphs after the election happened. They were based on pre-election polls. You can also make graphs like this based on exit polls, which are taken after the election, and you get similar results. We did it both ways. Pre-election poll, the advantage of exit polls is it's just people who voted. And also they have really big sample sizes, especially in battleground states. The disadvantage of exit polls is that they're kind of uncontrolled. Like you have non-response in telephone polls too, but non-response in exit polls is like can be a particular problem. And so it's really good to use multiple polling modes. So these particular maps I made from non-exit polls, and then the guy who criticized me found data from exit polls that contradicted my maps. His conclusion was I used bad polls, which was nice of him. The correct conclusion is I did bad statistical analysis. But he naively thought that I knew what I was doing with statistics. So he just thought I was using bad data. Actually, my data were fine, but I was doing bad analysis. But he'd not have the imagination to think that I actually just had screwed up in my statistical analysis.
Then we have another question related
Yep.
to A/B
Sure.
testing and election data. As a
Yeah.
statistician, when should you look for mistakes in the presented design or analysis or results? There may be some cases where the subject matter experts operate under some kind of bias on what the data should reflect. How can we remain impartial but open-minded as statisticians or data analysts in these scenarios?
Well, okay, let me postpone the first question, which is how can we, like, when should we be looking for mistakes, or more generally, how can we find more mistakes? The second thing is how to respond to people criticizing. I think that the, I don't get that much criticism. I mean, like people, like reasonable criticism, criticism with content is rare enough that every criticism with content anyone sends me, I look at. Okay, now if there's no content, they just say, "I don't like your map," or you're a shill for the Republican Party, or blah blah blah. Well, sometimes I respond to that and sometimes I won't. But if they have something specific, I will look at it. It's, at least in my experience, I am very far from the break-even point. Like I am far from the point at which the marginal benefit of looking at a criticism is negative. Because first, even if it's incorrect criticism, it typically means I have a communication problem. And so like it's already worth it, right? Like it's as a teacher, like as you know, as a teacher, it's always your fault, right? If they make a mistake, it means you didn't teach it right. And so, but then often there's errors. So I haven't, as I say, I haven't reached that point where I would have to triage the criticisms. I mean, it's really more that I want to get more criticisms. That's the way I want to change my workflow is to get more of this happening.
Okay. A few other questions, if you don't mind. So one is I'd love to use this as an example in a class I teach. Is this written up somewhere that we can access, including the plots?
Yeah, if here I'll put it in the chat. and then we had that. Now, unfortunately, the original ones were I have to get from the Internet Archive, but I had that. So give me 15 seconds while you prepare your next question.
Okay.
Wait a second. Oh no, here. Just sorry, it'll take me one. It just makes sense for me to do this to do this right now. It's gonna take 1 second to just find my search history. Okay.
In the meantime, there is a comment.
Okay.
That's a really important point. Just because a critic is a jerk doesn't mean they must be wrong. Hard to internalize, but important. So that's a comment.
Yeah. Well, I mean, I guess like I can think I think some version of this Internet Archive thing will work for the original graphs. Then you can follow the link and see the details. Well, I just think of myself, like I want people to listen to me even if I'm an asshole. And it's just that like there's a lot of experience where if you're not an asshole, people don't listen. I mean, of course you shouldn't be an asshole or a jerk. Like I try to be polite. Like I don't say like you fool, you made a mistake. I say like excuse me, but it's hard because people will interpret it negatively. If you look at the original comment that this person wrote, he wasn't actually rude to me at all. He was kind of dismissive. I took it as being rude. I was like, who is this guy? But when you look at it, he's really pretty specific. And so maybe that's part of it, is that like maybe the person isn't really being an asshole.
And then a related question is, Andrew, when did you internalize that?
No, I don't know, maybe because I'm the fourth child, I'm used to it. It's always been criticism is always good. I always liked it, and it's just hard to find criticism. It reminds me of what someone told me in graduate school once. They said, like, sometimes you're afraid that people are going to steal your idea. Don't worry about it. The opposite's going to happen. No one's going to listen to what you're saying. Like you'd be thrilled in academia if people would steal your idea, but it doesn't usually happen that way. So it's hard to get any attention at all. And so criticism is very good, and it's just I think it's mainly because when I write stuff, I give them to people and ask for comments, and people are usually too busy. So I appreciate when people put in the effort. Okay, I have like a lot more examples of learning from mistakes, but I think what I'll do maybe is now talk a little bit about principles. We can come back to examples if we want or we have time. So when you find out a mistake, you learn three things. And I'm going to describe them as past, present, and future. Okay. So past is something in your existing workflow led to your error. You did something wrong, right? So going back before the error that you have, there was a problem in your workflow. So you should trace your workflow, like a process tracing, figure out what you did wrong, and then see what happens and then alter your workflow. Right? Now that's the past. Then there's the present. The present is, I found a mistake, it's wrong, I got to fix it, right? And then the third thing is the future. Anything that flows, beliefs and actions that flow from your original statement might be wrong, so you should investigate your reasoning going forward and adjust to account for the error. Let me apply this idea in the two previous examples. So the Wikipedia example. Well, okay, let's first do, my very first example is redistricting. So implications for the past, what was wrong with my workflow? What was wrong with my workflow was that I wrote in the present tense, and I did not, more seriously, I did not think about the future implications of my work as a political scientist. I just wrote about the past, but then with an implication that was about the future. So that was wrong. So my workflow, the way to alter my workflow was to no longer to be much more clear about how we were extrapolating from the past to the future. What about the present? The original statement was wrong. Well, I'm no longer going around saying that redistricting doesn't matter, or redistricting is okay. So I've changed that. I no longer say that. I was really worried about that And I talked to a political science student about it, and he said, "Oh, don't worry, you shouldn't feel bad about that anymore." I said, "I shouldn't feel bad saying redistricting doesn't matter." And he said, "No, nobody believes your paper anymore anyway, so don't worry." And it's considered a classic, he said. It's a classic that nobody reads. Then implications for the future. Well, obviously, if I now think that, well, first, if I recognize that redistricting is a problem now, then it could be a problem in the future, and people should be, thinking about how to resolve it. Also, future, when I think of other people's research, I'm much more aware when I read a paper now to thinking about its extrapolative tendencies. Okay, so that's that. Wikipedia example. Implication for the past. Well, they had something in their workflow. There were two problems with their workflow. So workflow problem number one was that they were not actually randomly assigning the treatment, or they were missing half their data, or they had some big workflow problem, right? So that's important, right? If you find a problem, the solution is not to just fix that problem. You want to go back and figure out what went wrong, right? I would hate to think that the Wikipedia people are like, "Oh, that's too bad. We're going to white out that experiment and we'll just keep going everything that was the same before." How could that be? You obviously want to figure out what went wrong, right? It's like Boeing, right? You ground the fleet till you figure out what's going on, right? You don't say, "Oh, we had a bad plane. That's too bad. Let's take that plane out of commission," right? The present implications for the Wikipedia are, no, don't have to worry. It's not true that this treatment has a huge negative effect. The implications for the future, well, I have one more implication for the past, because there were two problems. Problem one was that they weren't doing the randomization that they thought they were doing. Problem two was that they had no quality control. They didn't know that they had a problem, right? Having a problem isn't so bad. It's having a problem and not knowing you have a problem is bad. So implications for the past, implication for their workflow is that they should not only improve their workflow so that they actually randomize their treatment like they're supposed to, they should also improve their workflow and have some diagnostics. And a lot of real world experiments, people do diagnostics to check that the randomization is balanced. I mean, it gets done. It's not like it's a shocking thing. Implications for the future, well, of course, it has to do with what are they going to think about the results of later experiments. With the polling example, my polling maps example, while my workflow had a problem, well, obviously I was using a bad statistical model, right? And so like the idea of fitting one model to everybody and another model to whites sounds clever, but it's not good because you lose this coherence. So that was the big, and also the way the maps were not so clear. The implications, the present implications were just, hey, throw out the old maps. These are better maps. I was making the maps to help understand how people voted. So it changed my understanding of how people voted to have better maps. The implications for the future were that I have to accept a certain additional modeling burden if I want to ask deeper questions of my data. So I realized that. So there's a saying in poker you don't evaluate the strategy, not the play. And in quality control, they say evaluate the process, not the individual outcome. Right. So this gets to my aim of this talk, which is how can we improve our workflow? So we want not so much to avoid mistakes, because I think that's impossible, but we want to be made aware. First, we want to be made aware of mistakes more. We want to be made aware of mistakes earlier. And then we want to know how effectively to learn from mistakes. So how can we do this? So how can we, so what are the tools that are out there? So one tool which is reproducible research. And I try to do more of that. I'm not so good at that, but I'm better than I used to be. I'm not as good as probably most statisticians because I'm old, so I have old school approaches. There are some really famous examples of non-reproducible research, like the paper by a couple of economists around 2011 called Growth in a Time of Debt, in which they made very big claims about economic growth and public debt. And it turned out that their entire paper was based on a mistake where they shifted two columns in an Excel file. It's known as the Excel error in economics. Well, that was bad workflow. If you have a good workflow, you're not you're not pushing columns around. You have a script. Even in Excel, you can have scripts. I mean, I think. They there are a lot of examples like that. There are a lot of examples where number of people publish papers and the numbers of the paper in the paper are inconsistent with each other. Where like you have data, a lot of fun examples. Like you have data that are supposed to have to range from 1 to 5, and they give you the mean of the data and the standard deviation of the data, and the standard deviation of that they give you, given the mean, is actually too large. It's like mathematically impossible to get. Like it happens all the time. So reproducible workflow, of course, well, that should reduce your error, but it's not just that it reduces your error. It means that when you find the error, you can trace it back better. I had an example, a paper we had to retract. It was called "Should the Democrats Move to the Left on Economic Policy?" And it was based on a very careful and clever analysis of polling data, except that we had accidentally reverse coded one of the questions. That goes from 1 to 5, and we had it but you have to flip to go from 5 to 1 because the yes is a more liberal response or more conservative response. I don't remember. Anyway, we did not flip it, and we should have flipped it. So we had to correct the paper. All our results had to be thrown out. Well, we had a reproducible we had a workflow in R, and so we could find the mistake, but it was ugly R code, right? So the cleaner your code, the easier you can find these problems. The way we found that particular problem was because we did the analysis, we published it. It was based on survey data from one election. And then I had a student wanted a project, and I said, replicate this, just do a bunch of past elections, and let's see how things change over time. So, and start by replicating the one we already did. So we replicated the one we already did, and we couldn't replicate it. So there you go. Well, that tells you another way that you can find errors, which is you have more people looking at things independently. So maybe one way to find errors is to make loud, wrong claims. So if I write a paper and say something that's really violates common sense and is possibly false, then lots of people on the internet will do me a favor and look at my data and try to figure out what I did wrong. If I say something reasonable, maybe they won't. So maybe if you want people to find mistakes, what you should do is write a very reasonable paper, but then like post it on social media with an inaccurate summary. Just lie about what's in the paper on social media. And then people will be so pissed, they'll go to the paper and try to replicate it. Now, it might be that they don't find any error because you're not trying to make errors, but at least you'll get more people looking, right? So maybe that would be good. And I just say this because often I notice errors when people make ridiculous claims, right? So those people noticed errors in my map because mine didn't look right, right? So that's another thing. Give people more handles, right? The more things, because if I had just described the results of my maps in words, maybe that person wouldn't have done me the favor of finding the mistakes because he wouldn't have noticed all the details. So you should be graphing a lot of stuff, publishing a lot of things, make yourself really vulnerable, and give people more things that they can check. So the more statements you make, eventually you'll say something wrong, which is what you want. Like you've already done your analysis. You want to say 80 million statements. And if you say 80 million statements and 400 of them are wrong, and people catch those 400, then you can maybe figure out what was going wrong because no analysis is perfect. Now, okay, more technical things. Prior predictive checking and posterior predictive checking. So you fit a model to data. Having fit the model to data, I can simulate replicated data and check that they look like the real data. Well, they won't look like the real data, right? Like my model assumes normally distributed errors. My data don't have normally distributed errors. Or my model assumes this. That's fine. Like your data don't have to be perfect, but you want to understand where your data, if you want to understand where your data are not fitting your model, where your model's not fitting the data, depending on how you look at it. So it makes sense for us to be simulating from the prior, which represents the prior predictive distribution, which represents the population distribution of all possible data sets we might see under our model, and also our posterior predictive distribution, because that represents future data that we might see if our model was correct, because it's based on the fitted model. You're not going to expect, your data won't look like every replicated data set, but if none of your replicated data sets look like your data, then you'd like to understand that. So that's something that we can do. I've been doing that for decades, and there was a time when Bayesians didn't want to do that because they had this attitude that my prior is subjective, and since it's subjective, you can't check it. And so since you can't check it, you shouldn't check it. Very strange thing. Usually you'd say my prior is subjective. I want to check it, right? That's more logical. But people had this attitude. Well, mathematically, it's true that you can't check all aspects of your prior. So that part's correct. But actually, you can check many aspects of your prior. It kind of depends on the problem. It's a lot of stuff that can be checked. And so once people had permission to check things, that helped a lot. Something else is, so it sounds similar, it's slightly different, and this is simulated data experimentation. So prior and posterior predictive checking, I have my data, I fit the model to data, then I simulate replicated data, and I look at how the observed data systematically differ from the replications. In simulated data experimentation, I have no data. I create a fake world. I always do this now. I never, well, almost never do I gather data without first simulating data. Now, why is that? Because I made a mistake a few years ago. It wasn't a fatal mistake to the project, but a mistake it was nonetheless. My collaborator and I did a survey. I won't go into all the details. We did a survey, and it was a before-after study. We did some causal identifications. We could kind of estimate a causal effect, not perfectly. I mean, you can read the paper and find out, but it was not unreasonable. We did a bunch of graphs and analyses. The key analyses had really big standard errors. So like I would say, like, there were some things that were two standard errors away from zero. Like I felt that we had some somewhat stable results, but the standard errors relative to the effect sizes were much larger than I was expecting to see. Like we barely got out of that project alive with some statistically significant results. Like, wow, what do I mean statistically significant? I hate that term. What I mean is that we had results that seemed stable enough that when they were published, people felt that we had learned something from our experiment. But actually, we had several different we're estimating several different public opinion issues, and we had enough data to kind of generally find an effect that we thought we might find, but we didn't really have enough data to distinguish between them. So our study was weaker than we thought. Now, why was it? Well, first, the effect sizes were smaller than we were expecting. Second, the standard errors were bigger than we were expecting. Third, we never had stated our expectations about our effect size and standard errors. We just ran it. We had a study with like 3,000 survey respondents. 3,000, that's a lot of people, right? Like we're estimating stuff. We didn't think about it. Now, if we had simulated replicate data, done a simulated data experiment, we would have had to hypothesize effect sizes, hypothesize variation, then simulate data, then fit our model, and then look at what we got. That's a lot of work. Well, first, it's a lot of work because like simulating data is a lot harder than analyzing data, right? It's like the difference between playing SimCity and writing SimCity, right? Second, so it's just work, right? Like, because also when you simulate data, you're not just simulating the effect size. You have to simulate all the regression coefficients you don't care about, all the predictors, like everything, right? It's like all the background, all the unmodeled data in your model still need to simulate. You don't have to simulate just Y given X. You have to simulate X also. Second thing, it was involve hard choices. Like, how big do I think the effect size is going to be? Well, this was a public opinion thing. The public opinion questions were in a 1 to 4 scale. So would I expect an effect of 1, like an effect of 1 on the public opinion? So that would be like shifting someone from a 1 to a 2, a 2 to 3, 3 to 4. That's a pretty large effect. Well, our particular treatment, like it's probably not good, like it won't affect everybody. Some people are already at a 4. You already have a strong opinion on, say, abortion, and manipulation's not going to change that. So most people won't be affected. Some people will be perversely affected in the opposite direction. You add it all up, I might say, well, maybe 10% of people are affected by the treatment. So if 10% were shifted by 1, that would be defective 0.1. Maybe that's not right, but the point is that already took work, and that's already getting me to these small effect sizes. If you say, oh, it's on a 1 to 5 scale, what's a large effect? Oh, 1, that's pretty big in a 1 to 5 scale. Oh, 0.3, that's a moderate effect. 0.1, that's a small effect. But no, that's not right, because an average treatment effect is an average and includes the average over all those zeros and everything like that. So would have had to work to do that. Then similarly, what's the variance? You have to make some assumptions about the variance. Finally, then we'd have to analyze the damn data, the fake data. Usually we don't decide our data analysis until we've seen the data. Now, that's not bad. Like, I actually think that's good. Like, I think it's fine to have a pre-registered data plan analysis plan, but in real data, you should go past the pre-registered plan, start looking at the data and doing stuff. It's less fun to analyze fake data. It's a lot of work. When it's all done, it's just fake data. You should do it. Ever since then, I always do that. Because then you'd see, like, under these assumptions, of course, they're just assumptions, but that's much better than not doing anything. Or when people say, oh, I did a power calculation. I looked it up. I found an online power calculator and I computed the power required. That's not enough because that's too simplistic. You have to just simulate your entire thing. So, oh, I can't simulate the entire thing. I'm a medical researcher. I'm busy trying to cure people. I just want to get NIH funding, so I'm going to run the online power cal. Well, no, it doesn't work that way, right? Like you have a statistician on your NIH grant. Like if your statistician can't do fake data simulation, then get a new statistician who can, right? Like this is it's a scam, right? I mean, if it's worth spending 5% of the budget of your study on designing the study so you can learn what you're planning to learn. Of course, that's still conditional on your assumptions, but the very act of making assumptions has value of its own. So let me stop here and just summarize. So I've made a lot of mistakes. We make mistakes all the time, and mistakes are unavoidable. We can learn so much from mistakes. I learned so much from mistakes. We can learn, when we learn from mistakes, we learn 3 things. We learn that our workflow is bad and we should fix it. We learn that I mean, not necessarily. Maybe you find the mistake right away and you say, I have a great workflow because I trapped the error. But usually you find the mistake, you realize your workflow is problematic. Second, you realize you just made a claim that's wrong or not supported by the data, so you have to unmake the claim. Third, if anything that's implied by that claim has to change. You no longer can assume blah, 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 blah. You might have to retract that paper or whatever. Now, one thing that frustrates me is a lot of people don't learn from mistakes. I get very frustrated. Like, for example, there was a book written by a couple of, I don't know, like academics, like, I don't know, business school professors, law school professors, people like that, called Nudge. And they talked about how you do this thing called nudging, and it makes people happier and better, and you don't have to tell them about it. You surreptitiously make their lives better. You're like some sort of, like fairy who can make people happy without them even knowing you exist. That book was they featured an experiment that was later retracted because the person who did the experiment had done a series of fraudulent experiments and he had to get fired. And he was not the author of the Nudge book. He was just somebody they had cited and said how brilliant he was. In the second edition, they took that out. But they did not have a page in the second edition, or even better, a chapter in the second edition, how we got fooled. They should have had that. There's an opportunity to learn from their mistake. They got conned. If you got conned, the right reaction to I got conned is not, oh, right? The right reaction is, I got conned. You can get conned too. We're big shot business school, law school professors, and we got conned, right? It's not a secret. Like, it's not a secret they got conned. They had to take it out. Everybody knows, but they didn't address it. They lost an opportunity. They lost an opportunity to learn what was wrong with their workflow that they could get conned, what was wrong with their claim, because if they cited this bad study and use it to make conclusions, maybe the conclusions are wrong. If the study didn't affect their conclusion at all, why were they citing it, right? Finally, implications for the future, maybe some of their other conclusions are wrong. And indeed, like there was later a Nudge meta-analysis that claimed large effects, but it was based on a bunch of crappy studies. And it's a whole field that's full of bad stuff. Not that everything is zero, but there's a lot of overclaiming. And people have avoided learning from their mistakes. Now, I can learn from their mistakes, but that's not as effective as them learning. Why don't people learn from their mistakes? I told you there are 3 benefits. You get to find out your work, improve your workflow, you get to change your wrong statement, and you get to improve your future. Those are 3 things people don't want to do, right? Because if you have to improve your workflow, that's work. And if you have to say your statement was wrong, you have to say I was wrong. And then if you have to change your implications for the future, you might have to change your entire research direction. So in that sense, there are good reasons for people to not learn from mistakes. So probably the number one thing is to not make yourself, don't be in a position where you're held hostage by your claims, right? You don't want your claims to be bigger than you. You don't want to be in the position like, I can't talk about what I did wrong because that would imply that my workflow is bad. You want to be in a position where you can improve your workflow, not where you've committed to something. And I do think there are methods out there. I have not thought about it systematically. This talk is the most systematically I've ever thought about this. It's just like good to have an opportunity to think about it. I think more can be said. The workflow as a buzzword is very popular. I like it. We're using it in engineering all the time. I and I think that in broad strokes, what I'm saying is very similar to the principles of quality control that statisticians like Deming and others from the 1940s wrote about. So it's not new, maybe it's me rediscovering this, but I've seen that I think I can learn a lot better. So I feel like what you should take out of this is if you can first learn more from the mistakes that you've already had, but second, if you can then tell your own personal workflow to reveal more mistakes and learn from more mistakes, I feel that this may have been an hour and a half, not completely wasted.